Today's video will demonstrate how to do red-black binary search tree balancing by demonstrating the same operations with a 2-3-4 tree. Hello, I'm James Helfrich. Most people find the red-black balancing of a binary search tree to be a bit difficult, and the case is to be difficult to visualize. However, most people find a 2-3-4 tree to be intuitive and easy. This video will demonstrate how both those operations are actually the same thing. Now, a 2-3-4 tree is a type of tree that has 1, 2, or 3 values in a given node. It's called a 2-3-4 tree because each node can have 2, 3, or 4 children underneath it. Now, a 2-3-4 tree is easy to manipulate and keep balanced, but it's not a binary search tree. Now, a red-black tree is another method of balancing a binary tree, and this is done by coloring each node as red or black. And the idea is you want to have a fixed number of black nodes from a given leaf node all the way up to the top. Now, these two look different, but they're actually exactly the same. So the 2-3-4 tree can be seen of as having black edges between each node. From the 16 to the 610, it's going to be one black node. From the 16 to the 24 will be a second black node. And it has red edges between values. So between 6 and 10, there's an edge. Between 20 and 18, there's an edge. Between 20 and 22, there's a red edge. So I'm going to draw this again, except this time I'm going to take the individual values in the 2-3-4 tree, and I'm going to separate them into nodes. And you can see now that the edges between 2-3-4 nodes are black, and the edges in between 2-3-4 values are red. I'm going to go one step further, then we're going to have the red-black tree. Now, it's useful to learn how to manipulate a 2-3-4 tree by adding and removing nodes, but it's a little bit less intuitive to do the same with a red-black tree. So we're going to demonstrate how these are both actually the same. Now, with the red-black tree, our case 1 says the root node is always black. So I'm going to add 100 to my 2-3-4 tree. I always add as red, and then because of case 1, I'm going to turn it black. And of course, for the red-black tree, I'm going to add a node. I always add a node as red, and then I'm going to apply case 1, and it becomes black. So these are both the same. All right, case 2 says if the parent of a given node is black, then do nothing. Now, with the 2-3-4 tree, I'm going to have the root node is 40, the left child is 20, and the right child is 50, and I'm going to add 70. So when I add 70, notice there's room in that 2-3-4 node for another one. In fact, I can have 3 values in a given 2-3-4 node, and I'm just going to leave it as red. Now, normally we don't color our 2-3-4 trees as red and black, but I'm going to do so just to illustrate the similarity between it and a red-black tree. Now, I don't need to do any work or any balancing because there's plenty of space for that 70 in my 50-70 node in my 2-3-4 tree. Now, back to my red-black tree, whenever I add a node, I always add it as red. Now, 70 is greater than 40, so I go right. It's greater than 50, so I go right. So I'm going to add the node here. Now I'm going to take a look at my case 2. Since my parent 50 is black, then I'm done. In other words, all the red-black properties are honored. Okay, case 3, if the parent of a given node is red and the aunt is red, then recolor the parent, the aunt, and the grandparent. So we're going to start in this case right here. Now notice the 2-3-4 and the red-black are the same. We both have the same root node, which is 40, the same left node, which is 20. In a 2-3-4, we have exactly one black value in a node. That value is 70. And in the red-black tree, we have the node 70, 80, and 50, where 50 and 80 are red. So we have the same setup here. Now I'd like to add 90. Now when I add 90 to the 2-3-4 tree, 90 goes to the right of 40. So I go to the 50, 70, 80 node. And oh, that guy's full. So what do I do when I'm full? And that's basically case 3. So the 2-3-4, I promote the middle guy, which is 70, up to the root. And then I reconnect him. Now I have 2 values at the root, so I'm going to have 3 children. And only one of these can be black. So 40 remains black and 70 turns red. Now I must have exactly one black value in a 2-3-4 node. So 50 and 80 are both going to turn black. And now that I'm finished, I can now add 90. And 90 is going to go to the right to 70, the right to 80, and it's going to fit right there. Okay, now we're going to actually do exactly the same thing. With a red-black tree, we only recolor, we don't actually alter the structure, which is kind of weird because in 2-3-4, we're going to alter the structure in this scenario, but we'll see how it's exactly the same. Now, first I'm going to take 90. 90 is greater than 40, greater than 70, greater than 80, so it goes to the right of 80. And now we're going to see that my parent is red, but my aunt is red too. Okay, so 50 is my aunt and 80 is my parent. So what am I going to do? I'm going to recolor 50 and 80 as black and 70 as red. Now I'm going to take a look at 70. Its parent is black, so I'm back to case 2 and I'm done. Now, the transformation looks a lot easier in the red-black than it did at 2, 3, 4, but we're going to see it's exactly the same thing because the root node for the 2, 3, 4 is 40, 70, and the root node for the red-black is 40, 70. And then we're going to see that the rightmost node of 2, 3, 4 is 80, 90, and then once again, 80, 90 is the same exact thing. All right, now we're going to get a little more complicated case. Case 4a and 4b, if the parent of a given node is red and the aunt is black or non-existent. So I'm going to start with this tree here, and I like to add 20. Now 20 is to the right of 60 in the 2, 3, 4 tree, so I go to the 30, 40 node, and it's going to go to the right of 30. So I'm going to add the 20 onto there. But now the thing is the 30 must be black, so I'm going to recolor 30 as black, and I'm going to recolor 40 as red. And now I'm good to go. Now we're going to do exactly the same thing with the red-black tree. So here 20 is less than 60, less than 40, less than 30, so it goes to the left of 30. And now we're going to see that my parent is red, so I'm going to do a right rotate. And what this means is 40 is going to come down, 30 is going to come up. And now I have to recolor my nodes. So 30 is going to become black and 40 is going to become red. When I'm finished here, we'll notice that the 20, 30, 40 nodes in the red-black tree correspond to the 20, 30, 40 values in that node in the 2, 3, 4 tree. The structure is the same. We have the same coloring for the same nodes. We've did the same thing. Now in the 2, 3, 4, I didn't alter the structure of my tree. I only changed the order within a single node, whereas my red-black, I actually changed the structure. One final case here. This is another example where a parent is red and the aunt is black or non-existent. So I'm going to have this case right here, and I want to add 30. So on the 2, 3, 4 tree, 30 is less than 60, so I go left, and it's going to go between 20 and 40. So what am I going to do? I'm going to scooch over that 20. I'm going to add the 30, which is going to become the new black node, and then I'm going to recolor the 40 as red. Now I'm finished. Notice how I only altered a single node, just like before. I didn't actually alter the structure of the tree. Now for the red-black, I'm going to add 30. Now 30 is less than 60. It is less than 40, but greater than 20, so it goes right down here. And now my parent is red, but I do not have a red aunt, so I can't go to case 3. So what am I going to do? Well, 30 has to be the middle, so 30 is going to come up and 40 is going to go to the right. Now, since 30 is the taking 40's spot, it's going to become black, and 40 is going to become red. There we go. Now our 2, 3, 4 tree and our red-black tree are equivalent. All right, so now we're going to do a demonstration of inserting into a 2, 3, 4 tree and a red-black tree. And we're going to see how they're exactly the same thing. Now, in order to illustrate this, I'm going to do them both at the same time. And I'm actually going to color my 2, 3, 4 trees with red and black so we can see the relationship. Okay, I'm going to start by inserting node 10. And with a 2, 3, 4 tree, we build from the bottom up. And I'm going to insert 10 here. Now now it's helpful to see that there's exactly one black node in a 2, 3, 4 tree. So I'm going to turn this to black. Now I'll do the same thing for my red-black tree. I'm going to insert a node 10. Now in a red-black tree, we build from the top down. And I'm going to, we always insert as red. Now note that rule 1 for the red-black tree is that the root is always black. Okay. Now I'm going to insert 20 for the 2, 3, 4 tree. And remember, every node can have 3 values. I only have 1 value in this node, so I can easily add it, no problem. Sorry, wrong one. Now, for a red-black tree, I have 20 I want to add. I always add as red. I go to the right, I come down. Now I'm going to try to balance on this guy. Notice how my parent is black. There's rule 2 for red-black tree. We have a black parent. We don't have to do anything. Now I'm going to insert 30 for my 2, 3, 4 tree. Now notice I can put 3 nodes in my 2, 3, 4 tree, and I'm just going to put it here. My black node is always, my middle node is always going to be black. There we go. Now I'll insert 30 to my red-black tree, 10, 20, 30. Notice my parent is red, therefore I have a problem. What rule am I? I'm not rule 1 because I'm not the root. I'm not rule 2 because my parent is red, it's not black. I'm not rule 3 because I don't have a red ant. Therefore, I'm rule 4, and our rule 4 is a rotation. So 4B is going to say that if I'm always on the right side here, then this comes down, this goes up, and this goes up. So now observe that rotations for a red-black tree happen within a single 2, 3, 4 node. Now this is the same here. 20 is in the middle, 10 is on the left, 30 is on the right. They're both the same. Now I'm going to insert 40 in my 2, 3, 4 tree. Notice my 2, 3, 4 node is full, so I'm going to have to promote this guy to the top, chink, and there's exactly one black element in every 2, 3, 4 node. And I'm going to draw my line down the left side of this, the right side of that, and I'm going to add 40. Now, for my red-black tree, I'm going to add 40 to the right, right here. Now observe, both my ant is red and my parent is red. This is rule 3 in the 2, 3, 4 tree, or sorry, in the red-black tree. So this means I'm going to recolor, recolor, recolor. And now for my grandma, I'm going to balance off this one, and that's rule 1. The parent, the root is always black. Now observe, we have the same structure here. Root, root, left, left, right, right. They're exactly the same. Now I'm going to insert node 60. 60 is going to go right, right, and it goes right there. Now the middle node has to be black, so I'm going to rotate, and I'm going to rotate. $60, right, right, right. Notice my parent is red. Therefore, I'm going to have the same rule that I had before, which is I'm going to have to rotate. So down, up, and up. So now they're the same. Now I'm going to put in 50. 50, oh, this is full. So therefore, I promote this up to red. These become black. And we go here. And then I'm going to insert 50 to the right. So I'm going to go 50, dink, dink, and then right here. Now, there's an issue here in that my parent is red. I'm not rule 1 because I'm not the root. I'm not rule 2 because my parent is red and not black. I am rule 3, and I'm 3 because both my parent and my aunt are red. Therefore, I recolor, recolor, recolor. And then I balance off this one. I'm not rule 1, I'm not the root. I am rule 2 because my parent is black. I'm done. Now I'm going to insert 70. 70, I have room, not a problem. Everything is cool. Red, black. 70, perfect. Notice my parent is black, therefore I'm rule 2 and I'm finished. Observe how the structure of the twos is the same. The height of the 2, 3, 4 tree is the same thing as the number of black nodes in the red-black tree. For every leaf on up, there's 1, 2, 1, 2, 1, 2, 1, 2 black nodes. Notice also that every black node is on top. Every black node is on top. Every black node is on top. 2 here. 40 has this one on the left, this one on the right. This one has these 2 here. And that's how we can see that every transformation we make on a 2, 3, 4 tree, we make exactly the same transformation on a red-black tree. Most people think of the 2, 3, 4 as a little intuitive, but the red-black allows us to implement it in the code. You can learn more about red-black balancing in the Insert section of the Binary Search Tree chapter of the Software Design textbook.